All right, so welcome everybody. My name is Seth Fox. I'm the worldwide leader of solutions architecture here, covering a team we call EC2 Core. I've been with Amazon Web Services about 5.5 years. I'm here to talk to you today about optimizing your cost with AWS Graviton based services. I'm also joined by Chad Schmutzer, who is one of our principal essays covering sustainability around Graviton. Today we're going to go through some slides just to sort of get us all on the same page about Graviton, and then Chad will come on and do a demonstration for us and sort of just demonstrate some of the stuff that we talked about today. So with that, let me take it away. So when we talk about broadest compute choice, right? AWS really does have a broadest and deepest range of compute choices in cloud. We have family of instances designed really for any workload. Whether you want to optimize for raw CPU cycles, maybe you need certain memory per CPU ratios, even high I/O storage and powerful GPUs. We have instance families that can help you with that. These families can then be customized, including a choice of processor, types of storage. Maybe you need ultra high speed networking, and even bare metal options for some of our customers that need that, giving you that really flexible choice around compute. We also have a broad choice of processors. When we started, we focused on Intel Xeon processors, right? We have the broadest choice around that. Over time, we've added more, right? We also leverage now AMD EPYC processors. These give our customers powerful and cost-effective options for x86-based workloads. And then finally, Graviton, which is what we're going to talk about today, our own custom-designed and custom-built silicon are the AWS Graviton family of processors. So let's dive a little bit more into Graviton and how our customers are working with it. So this is Graviton 3 processor was recently announced, went GA with our C7G instance middle of last year. That is the third generation of Graviton processor. It is custom silicon, like I talked about, and is based on the ARM64 core specification. And we designed this processor based on our understanding of cloud-native workloads. Having operated cloud services for some time, we understood what it meant to operate for our customers to use and build cloud-native workloads on AWS, and we designed a processor to meet that specific need. Why did we do this? Customers ask us all the time. It really allows us to rapidly innovate and iterate on behalf of customers. If Amazon's going to do anything, it's to make the customer experience better. And by designing our own processors in-house, we're able to make that cloud experience better for our customers. And when we look at it, the silicon innovation at AWS, right, we've been doing this for some time. Graviton is kind of the latest iteration of that, the Graviton 3 processor, but we've been building the Nitro system and working in that Nitro system for a while. The Nitro system really covers our hypervisor, Nitro SSD cards, network storage, SSD, and security as well, right? So these are some chips that we designed to sort of handle those pieces to sort of become the hypervisor for our platform, which I'll talk about here. And then the AWS Graviton is sort of the manifestation of that as a general purpose compute processor for allowing our customers to run and build powerful and efficient modern applications on AWS. So what is the Nitro system? It's a combination of hardware and software, right? These are chips that we've been building with Annapurna Labs. There are 5 generations of these now, right? This is something that we've been doing for some time. The Nitro system overall was introduced in 2017 with the C5 instance. We did start doing components of these chips that were designed with the C3 for enhanced networking in 2013 to get higher performance, lower latency, things like that. And we've expanded over time with other I/O and newer Nitro cards that have been revised over the course of the AWS history. We also built a hypervisor. We rebuilt the hypervisor from scratch to really remove a bunch of that functionality. And effectively, since 2017, if you're launching an EC2 instance that was launched after that, you're already using Nitro. It's something you already have in place today. What are some of the benefits, right? First, Nitro helps us really better secure our EC2 instance, right? Security is job zero here, and this provides us some unique security capabilities, like Nitro Enclaves as one, and line rate and networking and storage. Second, Nitro makes it easy for us to turn any server into an EC2 instance. It gives us that level playing field across all the different hardware platforms. This is how we're able to provide so many instance options like Intel, AMD, Graviton, and even Mac hardware that we have available today. Of course, Nitro also helps us improve performance, and by running all of our AWS code on the Nitro controller, we can allocate all the resources of the EC2 server to customer workloads, right? And I have some diagrams to sort of show what that migration from Zen looked like. But this is designed to provide us the highest performance because it completely eliminates the virtualization overhead that existed before. Nitro does help us with performance in other ways, but by doing all of our network and storage virtualization on the Nitro controller, we reduce performance variability because we can use dedicated resources and optimize hardware. These improvements to performance also bring sustainability benefits, which we'll talk a little bit more about, by increasing utilization and reducing the energy costs across our fleet. So what did the environment look like at AWS before Nitro, right? We used Zen. Zen is great. It did a lot. It ran with our customer instances on the host CPU. It did memory management, CPU scheduling, device emulation, and all the things a normal hypervisor does. In a typical data center, 20% overhead is what you sort of give to the hypervisor. These functionalities, and you give that overhead because these functionalities are all running on the host CPU. So what we started doing is offloading these capabilities to dedicated hardware devices. Right, so we started with Nitro cards. Right, these helped us do that VPC networking, connections out to EBS. Nitro SSDs were also something that we built, and then system controllers. Right, the idea here was then we sort of moved on and replaced Zen with a very lightweight hypervisor. Right, and here what we're able to also do is provide a Nitro security chip. Right, the Nitro security chip provides a simple hardware-based root of trust. It's able to measure the contents of flash devices on the motherboard, so we can be sure we're running the firmware we expect. It monitors all the hardware interfaces and blocks unauthorized modifications. And we designed the Nitro system to ensure workload confidentiality, not just between customers and AWS. There's no mechanism in this system for any other system or any person to interactively log in to an EC2-based server, right? There's no root user, there's no interactive access, and there's a narrow set of authenticated and authorized APIs that are logged so that we know that nobody has access to customer data, right? That's what the Nitro system is able to do for our customers. So what does it look like now? We've built Nitro. What does it look like now? So we've taken that Nitro card and taken those main pieces off, including DOM0 from Zen, and put them into that dedicated hardware. We have a very thin hypervisor that really does some memory management, security functions, right? Things like that. It handles those pieces. But now we have a host CPU that is really dedicated to our customers, right? So now we have this environment where that hypervisor overhead has gone away, allows us to reduce costs. It also increases sustainability because now we can get more instances into the same footprint. So a little bit of history of Nitro, right? We've been building Nitro for over a decade. And over that time frame, we've released 4 different generations of Nitro chips. Each subsequent generation improves on the past along many important dimensions, things like lower latency, higher throughput, ability to handle more packets per second. We've also added new features like line rate VPC and storage encryption. Performance can be hard to improve when you don't want to budge on things like security, cost, and power efficiency, but that's exactly what we did with our first 4 generations of Nitro, right? And then we were able to do, for those that attended reInvent, this is something we just announced, Nitro version 5. This Nitro chip continues to deliver significantly on that improved performance. Nitro V5 coming in with about twice as many transistors as the previous generation Nitro chip, and it gives it twice the computational power. It also has 50% faster memory access and a PCIe adapter that provides twice the bandwidth. What does this mean for our customers is that Nitro V5 now supports 60% higher packets per second with 30% reduction in latency. My favorite part about this is we've done all of this while lowering the power consumption compared to Nitro V4, right? Sustainability is something that has been very important for our customers. And I want to talk a little bit about one of the initiatives is the climate pledge that Amazon has taken, right? This is our sustainability transformation. We started this in September of 2019 when we announced this climate pledge with global optimism. This was a commitment to be carbon net zero by 10 years before the Paris Agreement, which was set 2050 as the goal. Our public goals on this, you see listed here, net zero carbon by 2040, powering operations with 100% renewable energy. We initially committed to reach that by 2030, but we're now on a path to meet that target by 2025. We also set up a $2 billion equity fund so that we can help the world find solutions to this difficult to decarbonize problem. So how does Graviton help with that specifically? Right? We talked about Nitro and the direction we're going there. Graviton instances, are 60% more energy efficient comparable to comparable EC2 instances. How do we get that? Higher efficiency, density for one, right? We're able, because we're designing the processor, we're able to design more dense environments, and that was able to lower cost, and in turn lower the carbon footprint. When we look at Graviton 2 processors, these are up to 3.5 times better performance per watt. And for those that are familiar with our well-architected framework, we added a sustainability pillar to that a while back, and we also have a carbon footprint tool. So sustainability is super important. Graviton is key to that, and there's many parts of Amazon that are trying to help our customers grow in that space. So what does Graviton look like, right? If you're using instances today, whether they're general purpose, storage intensive, memory intensive, things like that, you'll be very familiar with the way the Graviton instance families are laid out. It's the memory to CPU ratios that you see for x86 have been translated into Graviton, and you can look and see the lowercase g tells us that these are Graviton instances. So whether you need something to run high memory workload or a GPU-based workload, looking for that lowercase g will find you what you need, and it will map very nicely into the work that you're doing with your instances today that are mapped to your workload. That being said, what workloads do we see running on Graviton? They've been pretty broad, right? And we look at everything from web and gaming servers, microservices, container-based applications like Chad's going to talk about today, analytics. We're going to see some stuff today on analytics as well, in memory caches. I encourage everyone to take a look at the customer references we have. There's a lot of industries that are taking advantage of Graviton. It's getting broadly adopted across many different workloads with our customers. Now, that being said, if you need more than EC2, maybe you're using some of our managed services, right? You're using Aurora or EMR. EMR is going to be a demo that Chad's going to show us here in a few minutes. But the idea here is you're able to consume Graviton underneath these. When you look at this, you're going to see that you're really consuming the API of, let's say, RDS or EMR is the demo that we're going to see. You don't have to sort of concern yourself with the underlying CPU architecture, and you can very quickly get that cost and performance benefit that our customers are seeing from Graviton-based instances. Now, for those customers that are running different EC2 instances, the operating systems that are supported today across Graviton are pretty broad. Everything from Amazon Linux 2, Red Hat Enterprise Linux 8.2 or later, SUSE 15 SP2+, and then Ubuntu 18.04 and 20.04. Right. The idea here is you want to be in the newer versions. That's where you're going to see a very big trend for a lot more ARM efficiencies that have been built into these applications. When you look across the container ecosystem, another demonstration that Chad is going to do is going to be Kubernetes, right? The container ecosystem has broad support for Graviton as well. Whether you're using Kubernetes, ECS, or EKS, you can definitely get your workloads up and running on Graviton. Other Amazon tools, maybe using cold build, code deploy, also be part of our demo today, are also services that you can use with Graviton, and we'll support that. If you're using Java, we've got a supported JDK, things like that all work on Graviton. And these are sort of the AWS tools that are in the market that customers are using with the Graviton support. Now, that being said, we do have a lot of customers that are using third-party ISVs, right? We designed a program called Graviton Ready, AWS Graviton Ready program. This is designed for ISVs to signal to their customers that their applications work on Graviton. So maybe you need a virus scanner. Trend Micro has a solution in that space. They have an agent that works on Graviton-based instances, and you can consume that in your environment. So a couple things there. One is, take a look in this program. It's on our website for sure. But if you have an ISV maybe that isn't working on Graviton today and you're struggling with that, reach out to your account teams and they can come back to Chad and I, and we can help get that going. That's one of the things that we do here for sure. In terms of ease of adoption, this is another question that comes up a lot as well. Like, how hard is this to do? I've got this application. I've been running it in an x86 environment for years sometimes, right? How am I going to get this onto Graviton, into an ARM processor? So we tried to make this a fairly simple approach, everything from quite easy to things that just don't work yet. When you look in the Linux workload space, which is where we're going to start, if you're talking about an interpreted language like Java or Python, PHP, Node, things like that, these things are pretty easy, right? You want to find the right base image that works. You want to make sure you're using the right version of Java, right? Java 8 was the first one that included support for ARM, but you'll see a lot more as you get closer and closer to current Java. The ARM performance improvements are there, right? Are greater. So something to keep in mind. Being current or at least more modern is very important as part of this process. But things to look out for: JNI, shared objects. Maybe you've got something compiled underneath that really is designed for a specific processor architecture. That's an important thing to look out for as you're doing that and going through that environment. Things get a little bit more involved, but still not hugely complicated, right? Maybe you've got a compiled language like Go or C, C++, right? So here you have to cross-compile, right? You maybe before you build your container, you want to cross-compile this and get this going. Here are the gotchas. You want to look for any intrinsics. Maybe you've done something in assembly, things like that. You want to make sure you're getting those pieces and capturing those. But the reality is, Go is really designed to be very portable, and it's part of its attraction to a lot of customers. And getting that cross-compiled can be is definitely something to look out for, but is not the most complicated thing. Another area we see is .NET. Right, if you can run .NET on Linux, right, getting that up and running, there's a lot of reward there, and getting those things up into the environment. You know, a good course of action there. If you're running it, if you're running that today, let's get your Windows, getting off of Windows into Linux on x86, and then looking at the moving over to ARM, so that you're sort of getting it's a idea to do science, right? Keep it some real science and go one step at a time as you make those migrations, but we see a lot of customers get a lot of reward out of that. Today, Microsoft Windows Server is not yet available for ARM64. We'll keep an eye on that happens, but right now there are no Windows server images available for ARM64, so it really is looking at Linux only today. With that, let's move on to the demonstration. This is why everyone came here today. So I'll turn it over to Chad, and he can talk to us about EMR and containers on Graviton.
All right, thank you, Seth. Really appreciate that presentation. Again, my name is Chad Schmutzer. I am a solutions architect focused on sustainability with Graviton instances, and it's great to be here today. I really love that slide where you talked about the different levels of adoption for Graviton. That easy level, that first tier, is the one that makes me excited, and it's really what this workshop is about today, this demo that we'll be going through. It's about the ease of adoption of Graviton and how easy it is to integrate Graviton into your workloads, including Graviton and big data with Amazon EMR, and Graviton and containers using both Amazon EKS and Amazon ECS. So let's get started. So we'll be doing sort of this run through of a workshop / demo, and the really neat thing about this is that the workshop that we'll be using is actually a publicly available workshop, and the URL is right here, graviton2-workshop.workshop.aws. If you browse to that, you'll come to this page. Again, publicly available. Anybody can do this in their spare time. And if you'd like to follow along in real time through this, you're perfectly welcome to. Otherwise, if you want to watch the video and then head back and run this, after the fact, or follow along sort of side by side, you're more than welcome to. Just please remember, anything you spin up, will in your own account will incur charges, and so we highly recommend that you sort of spin things down, shut things down after you've completed the steps of the workshop, to make sure that you're not paying for things that aren't currently being used. Okay, so let's get started here. We'll start with the Graviton and Big Data workshop. I do want to call out a couple of things. So in order to work through this workshop, we can jump to this Getting Started page, which talks about how to set up an IDE environment and to get your environment prepped to run through the steps of these workshops. So the first thing to note is that we want to set up a workspace, and that workspace we'll use is called Cloud9 IDE. It's the Amazon Cloud9 IDE, which is a really awesome environment where you have an IDE built right into the AWS console. I've spun my Cloud9 IDE environment up already. You can see that it's running here. It's in my account. if we look at the instructions walk us through the entire process of even launching your Cloud9 IDE. So that includes picking the appropriate instance type to use for your IDE environment, setting up your networking, and as well as setting up appropriate permissions for the IDE. Because from the IDE, we will be making calls back into AWS services and resources, and we want to make sure that all of the appropriate IAM permissions are in place so that we're operating in a secure manner, and that we can make the calls that we need to make likewise. So again, the IDE is fantastic. As you can see, it's here. It has a built-in terminal. It has a file browser. It has a file, a viewer, a text editor, everything we need, a one-stop shop for getting through this workshop, and for any of your AWS needs where you need a modern IDE, in the cloud. Okay, so a couple more things. We have some prereqs that we need to work through. And this includes cloning a publicly available GitHub repository just for this workshop, right? So the repository is here. It's listed in the prereq section. You can simply clone this workshop into your IDE and get started going quickly, right? The one thing, I've executed these steps already in the interest of saving time, but I will explain briefly what was done. First thing we want to do once the repository has been cloned is to go ahead and make sure that your tools are up to date. So in this case, I updated the AWS CLI that comes on the instance. Just making sure that it's up to date is always a great idea. I installed a few additional tools, including JQ and Bash completion tools, just to make our commands a little bit easier to run. I also installed Kubernetes tools for interacting with our EKS cluster, and that includes downloading kube control, installing it in a user local bin on our IDE, and obviously giving it execute permissions so we can utilize it. And then finally, in the terms of the prep stage, setting some account and region environment variables so that we can make sure that we're operating in the appropriate region from a command line perspective. We want to make sure that all of our environment variables are set up and we've configured everything properly, and set up the appropriate roles that we need for any of the applications that we'll be deploying here. For the EMR portion, we will be using SSH. So we will go ahead and set up an SSH key using keygen, and then we will copy this key up into our AWS account so that it's accessible. And finally, from an IDE perspective, the IDE is resized. We install Node.js. We get a Python virtual environment set up, and then we install a couple of additional requirements. And finally, we bootstrap our environment using the Amazon CDK. So the two main tools, again, for this workshop include the Cloud9 IDE and the Amazon CDK, which is the Cloud Development Kit. And you can learn more about that here at aws.amazon.com/CDK. All right, so let's get started with Graviton and big data with our first workshop. So essentially what we'll be doing in this portion is we'll be exploring running Amazon EMR using Graviton instance types. As I mentioned earlier, easy thing to do. EMR natively supports Graviton instances. And so in this scenario, what we really will call out is that there's really nothing special or additional to do to take advantage of the power of Graviton within your EMR environment. If you're not familiar with EMR, EMR is an easily run and scalable environment to run Apache Spark, Hive, Presto, and other big data workloads. It's a very easy service to use, built-in integration with many other services, and in order for you to do a full end-to-end, big data workload and workflow. And again, the point here is that it has native support for Graviton, and through this workshop, we'll see how easy it is to utilize Graviton within EMR. And we will be running through a scenario of running a very simple Spark job on our EMR cluster that we will spin up. So let's talk about the steps we'll use to get going here. First thing we'll want to do is we'll want to create an S3 bucket that will have an input folder and an output folder that will include, the input folder will include some source data that we'll use for our Spark ETL job, a very simple data set that we'll review here in a few minutes. But we'll set that environment up in terms of the S3 bucket, and then we will launch a job on top of our EMR cluster that will point at that S3 bucket for both the input and output data that will flow in and through our ETL Spark job. So let me pull open this file here. we'll execute the script that's in the directory that the repository that we cloned from GitHub. And what this does is it simply creates a bucket. It blocks public access from it. Something that you always want to remember to do with S3 is to make sure you don't create any publicly accessible S3 buckets. Lock down those permissions immediately. And it will create 4 folders: an input, output, files, and logs folder. And then it will copy some sample data into the input folder. And this data is called tripdata.csv. I'll open up that file and show you what's in it here in a moment. But just keep that in mind as we execute this script in our IDE here. So let's go ahead and copy this and execute this in our environment. And we can see that our script has executed, and we have created our file, our S3 bucket, and we've uploaded our sample data into the input folder within that S3 bucket. Next thing that we'll want to do is we'll want to go ahead and create the EMR cluster. It's very easy to kick off. I've already executed this step because it does take a few minutes to kick off and deploy an EMR cluster. But in the interest of saving time, I've already gone ahead and done that. But just to show you how simple it is to utilize Graviton within our cluster, the first step is to go ahead and make sure that those default EMR IAM roles exist, and there's a command for that from the AWS CLI, AWS EMR create default roles. We will stash the subnet ID that we're working in into an environment variable so that we can tell EMR where to deploy within our VPC. And then we'll go ahead and finally go ahead and launch the EMR cluster using the AWS EMR create cluster command. And you'll see it's quite easy to do. We give it a name. We ask it to use those default roles that we just created. We will choose the version, in this case, 6.1.0. We'll ask it to utilize 3 instances, give it an instance count of 3, and we'll use the instance type of M6G.4 extra large, which indicates the M family with Graviton processors of 4 extra large, and this defines the size of the instance type. And so since we're asking for 3, those 3 will be distributed across the head node and the core nodes within the EMR cluster. And it will do all of this for us under the hood. So very easy to get started using Graviton within EMR. We will ask it to include the following applications: Spark, Hadoop, and Zeppelin. And then, of course, the EC2 attributes, which define which subnet ID to use and which SSH key to use for launching our cluster. That's it. That's all you need to do to launch our EMR cluster. Again, I've already run this command. So let's go ahead and look at the next steps. And while we kick off the job itself, I'll then come back and revisit the data and all of the different pieces of this ETL job, this very simple Spark ETL job. So let's go ahead and look at our next steps. First thing we want to do is authorize a connection to the cloud, to the EMR cluster from our cloud instance. So these steps essentially allow us to go ahead and configure that so that we can shell SSH into our cluster. Next thing we want to do is go ahead and copy the job itself to the head node. We'll do this with this command. It's just an SCP command. I will go ahead and execute this as well. And this has now copied the ETL Spark Python job into the head node of our cluster. And finally, let's go ahead and connect to the EMR head node and kick off that Spark job. You can see it's in an SSH command. We call the ETL Spark Python script, and then we have an input S3 bucket folder, and then an S3 output S3 bucket folder for the output. Again, quite easy to kick off our job. Let's go ahead and execute that. As that gets going, there we go. Our job has been kicked off. It's now executing on our EMR cluster. I will now head back and show you what we've done. All right, so heading back a step, remember earlier I told you that we copied some sample data to use for our Spark job into our S3 input bucket. So let's take a look at what that data is. So that data was called tripdata.csv. It's a very standard CSV file. It's basically a capture of some New York taxi data logs from back in 2017, just an example data set that we would maybe use for using for analyzing on an EMR cluster. We'll utilize Spark to basically dissect this file and crunch some numbers against it and then spit the outputs out. So the job itself, as we can see here, is basically a very simple Spark job, and we can open that up as well and take a look at that job. So that's the ETL Spark job. So this Spark job simply starts a Spark session utilizing the New York taxi data CSV file that we mentioned earlier, and that is sourced from the input folder, which again is an S3 bucket that has an input folder in it that has the data that we created earlier in the step. After that, we go ahead and kick off our Spark job here. And this Spark job is simply counting the total number of records in our data set, all right, in our CSV file. That output will then be saved, written into the output folder of our S3 bucket in Parquet format. So again, very simple end-to-end Spark ETL job, complete with the input and output folder. And we've executed this job on our EMR cluster. Now let's head back to the console and take a look at how we did here with EMR. So this is the EMR cluster, and I just want to sort of drill into it a little bit just to show you what we've done. If I click on the cluster ID, we can see that this cluster is in fact already running and waiting faithfully for us to send it to jobs. We can see that it's powered by one head node and two core nodes. Again, both Graviton instance types, very easy to run, very easy to do, and nothing else besides telling EMR, asking EMR to simply use these instance types. From an application perspective, we can take a look here at the fact that we launch these jobs. We can check the Spark history server as well as the Yarn timeline server. Let those open up here, and we can see the history of those jobs. While those are opening up, let's check the S3 console. Let me reload here because we just created a new bucket, and we'll take a look at that new bucket. So there we are. So this new bucket is the Graviton EMR Lab bucket. And we can see inside of that bucket that it has those 4 folders that we talked about, including the input folder that had the trip data. And it has an output folder that includes the Spark folder and the fact that we have a success file written out. And then we have the Parquet file that was the output of our Spark ETL job. Let's go back here and take a quick look at our application history. We can see the job that we just ran. We can, using the Spark history server, we can drill into the application ID, and we can get a good view of what happened on our job on our EMR cluster. So again, very simple to use. Very, very intuitive in order to use Graviton within our EMR cluster. And again, I hope you consider and think easy when it comes to using Graviton with EMR. All right, so let's just make sure that we call out. I do recommend that you terminate your EMR cluster and delete your S3 bucket after you've done this to save costs, to make sure that you're not paying for anything that you aren't using. So there's a simple command here to delete your EMR cluster in the workshop, and I highly recommend that you also empty and clean and delete your S3 bucket that you use for this workshop as well. All right, so let's head over to our next exciting session on Graviton and containers. Again, keeping in mind ease of use with Graviton and containers. In this workshop, this first part of the workshop, we will talk about how easy it is to deploy a multi-architecture environment on Amazon EKS using both x86 and ARM64 Graviton-based processors within the same EKS cluster. And we will actually build an entire end-to-end pipeline using Amazon EKS, Amazon ECR, and AWS developer tools, including code build, code deploy, and code pipeline to power this end-to-end environment. So let's take a look at the steps here that can help us get started quickly doing this. So the first thing to call out is that we want to consider the fact that we don't want to have multiple, we don't want to build things twice, right? We want to have a single pipeline that'll build our application for both architectures, for both x86 and ARM64 at the same time. So our pipeline will be set up to handle that, right? So we want to have a single application environment that we can commit to a repository that'll kick off a code build and then deploy, build and push our container into a registry and have them ready to go for our deployment. So we can see here from this sample code in the case of where these are set up here in our pipeline configuration, which is the the AWS CDK code that is used to define our pipeline. So let's take a look at this visually. What does this look like? What this does is the end-to-end container build pipeline includes an AWS code pipeline that powers sort of the succession of this whole thing here. It has a code commit repository that is configured for us to utilize. As we push code into the code commit repository, it automatically kicks off a code build for both architectures at the same time. After those are completed, it then takes that architecture manifest and then pushes those into Amazon ECR, which is our Elastic Container Registry. So we will have Docker images for both architectures built at the same time in our pipeline, and then ready to use for application deployment on top of EKS. So the command that we used to deploy this pipeline is the CDK deploy Graviton ID pipeline. I've already done this because it takes a few minutes to set up. And I can show you the configuration file for this in our IDE environment. Let's take a look here. So the pipeline CDK pipeline file here, and the things that I will call out are the code build actions, the Docker build code actions for both x86 and ARM64. So this is where we set up our pipeline stage for both architectures at the same time. And then here's the manifest stage, which outputs the files up into the ECR container registry. Okay, so let's take a look at our next step. Since that pipeline has already been built, I will show you what it looks like from the console, but let's just kind of walk through the next steps of utilizing that pipeline from the CLI. In this case, we will have changed into our workshop directory. We will go ahead and clone the empty code commit repository. We will then copy our sample Node.js application source code into the new repository, and then we will push that code back up and make a commit back into our code repository. Doing this will trigger off a series of steps, right? It will build Docker images for both x86 and ARM64 architectures. It will build the Docker image with multi-architecture manifest, and then it will push all of those images into the ECR repository. And again, the code pipeline takes care of all of this for us, and we can jump over here to the pipeline within the AWS environment just so we can have a look here at this from a visual perspective. Code pipeline. Okay, so we have our Graviton 2 pipeline lab, and again, just a nice visualization of looking at the code commit step, moving on down to the Docker build step that includes both x86 and ARM64 at the same time, and then finally the manifest step, which takes those images and pushes them up into ECR. So we have a complete pipeline that has built our source code and stashed them in Docker images, and then makes them available for deployment in further steps. So again, I've already executed these steps, and what we'll do next is we will go ahead and set up some additional environment variables so that we can then utilize what we've built already to go ahead and kick off the next step, which includes launching the EKS cluster itself, and then getting ready to deploy an application on top of that cluster. Okay, so let's take a look at the CDK code for deploying our EKS cluster. This is the part that I'll call out where we can see the cluster configuration, specifying our Kubernetes cluster values, as well as the virtual private cloud and the security groups, as well as the two different node groups, right? We have an x86 node group that will be using M5 large instances in, and then a node group for ARM64, which we will be using M6G Graviton instances inside of. And each of these node groups, we will be asking for 2 instances to be deployed to power our EKS cluster. And I will pull this file open here in a second, but the command to go ahead and deploy that cluster using the CDK is CDK deploy Graviton ID EKS. And this step typically takes roughly 15 to 20 minutes to deploy our EKS cluster. I've already done it because I wanted to save some time, but we can take a quick peek at the CDK configuration for the EKS cluster within our IDE as well. And we can see again some additional parameters that we set up with our security group, as well as defining our endpoints. And the most important part here is the node definitions for each of the architectures that we will be utilizing. So again, I've already kicked off this deployment, and our Amazon EKS cluster is already up and running in my account. So let's just check it, right? So let's use our cube control to get an idea of what our cluster looks like. First thing we'll do is we'll stash some information about the cluster in our configuration so that we can then make a call against it. So the next step is to go ahead and test the cluster and verify that our nodes are running. And this is my favorite part here, where we ask Cube Control to tell us, hey, give us a list of the instances that are running and tell us the architecture type. So here we have 4 instances, 4 EC2 instances running, all in the ready state. And we can see that the architecture, we have 2 of them that are AMD 64 and 2 of them that are ARM 64. So again, we have our multi-architecture cluster up and running and ready to go, ready for us to jump to the next stage, which will be to launch an application on top of this EKS cluster. So here we are. So now we're ready. We have our cluster set up. We have our nodes set up in EKS. It's time to put an application on it and show the power of the ease of use of this cluster that we've just set up. So we have an application, multi-architecture Kubernetes application, a deployment manifest. We have some of the highlights of that file included here. I'll just call these out here. That this includes the entire application stack, including both architectures called out here in the values of this configuration. So let me go ahead and launch this, and then we'll take a quick peek at what these files look like. So let's go ahead and initiate our deployment. I'll just copy these commands here, execute them in our IDE. Kick off the deployment, because it does take a couple of minutes for the load balancer to come up and become available from a DNS perspective. We can check on the status of our deployment using the cube control command of get service and the deployment for the multi-arch namespace. So let's go ahead and just make sure that everything our application launched appropriately. Okay, so we can see that we do have a load balancer, right? A network load balancer that was launched. It has its external IP already defined here, so it'll just take a few minutes for it to become available from a name resolution perspective. And we have 4 pods that have been launched on our EKS cluster, and all of them are ready to accept traffic and are sitting behind the load balancer. So let's take a quick look at again at the application the deployment manifest. We can take a look here. So this manifest includes, as I mentioned earlier, deploying a network load balancer. It defines the ports, both the external and internal ports for the containers, the load balancer and the containers to forward traffic to. And it also includes the fact that it's utilizing both architectures, and it's giving us a pointer at the source for the images, which lives in Amazon ECR. Okay, then we will also take a quick peek at the EC2 console, because I love to look at the instances that are powering our cluster. So if I take a look over here, we can see that we do have the two M5 larges and the 2 M6G larges that are running and powering our Graviton cluster. EKS cluster slash x86 cluster, if I drill down into one of these and I take a look at the tags, we can see that in fact this is one of the EC2 instances that's powering our EKS cluster, and just another view of looking at the underlying compute power that's powering our EKS cluster. So let's jump back to our IDE and see if our load balancer is resolving its name yet. We have a command over here that we can use from the CLI, where we can simply query the ELB about 8 times and just let it respond to us with our application that's running. Let's see if the load balancer is resolving its name yet. Not quite ready to go, so we'll give it another second here to finish its name resolution. And while it's doing that, let's just take another quick look at the EKS console. We can see that our Kubernetes cluster is running here in the EKS cluster. We can drill into it and look at all kinds of information about it. We can also have quick links to both Amazon ECR, and if you wanted to do some batch processing, you could use batch here as well on our cluster. But again, a quick stop shop for understanding all things about our Kubernetes environment, as well as associative resources for our cluster. So let's head back to our IDE. There we go. So our load balancer, we've called it 8 times just for fun, and we can see that each call is communicating with a different pod, and each of these pods could potentially be running on an ARM64 processor or Graviton or an x86 processor. And we can see that we have, and sure enough, this simple Node.js application, its entire job is to just tell us what processor architecture it's running on. So we can see we have a nice randomness to it to show us that we're running across both architectures at the same time. So very cool, very exciting. So let's go ahead and head on to our next step, which is also a fun part, which is let's take a moment to do a failure scenario on our EKS cluster. And so what we'll do here is we will actually force the single architecture use within our EKS cluster. So we'll scale down the cluster with a number of replicas to 0. We'll pin the multi-architecture container environment to a single architecture, and then we'll scale it back up. So just for fun, let's go ahead and do that and let EKS do its thing. We'll kick that job off there, and we can come back and we can check the status of our application now that we've messed with it a little bit to simulate a failure scenario. And so let's go ahead and execute this kube control command to get the pod status for our environment. Okay, so we can see that EKS is doing its thing. It's has a couple of jobs in pending state and a couple of pods that it's terminating. So it's working itself out. It's adapting itself to the failure state that we've thrown at it, and allowing it to adjust itself. And ultimately, what we should see is that two of the pods should be ready to go. And 2 of them should be in either a crash loop back off state or an error status, because those cannot be started due to the fact that we've reduced it to a single architecture. And so we can see here that we do have 2 pods running and 2 are in crash back off state. So demonstrating the resiliency of EKS if in fact we were to lose one of the architecture types, just as a fun example here. All right, so I hope that was an interesting and great overview of learning how to deploy a multi-architecture EKS environment, as well as a multi-architecture application on top of that environment. Within the workshop itself, there are steps to also do the same process in terms of running an ASP.NET Core application on Graviton 2. I'm going to skip this step in the interest of time, but do know that it does exist. So if you're a fan of .NET and want to learn a bit more, I do highly suggest that you just spend a few minutes on these steps here, which shows you the full pipeline, but specific to .NET Core builds on top of Amazon Linux 2, which is a pretty slick thing to do if you have a .NET Core 5 application environment. We'll skip to the next step here, which is to demonstrate the ease of use of deploying Graviton 2 processors on ECS. So ECS, if you're not familiar with it, is the Amazon Elastic Container Service. It's a highly scalable, fast container management service. It's super easy to use. There's a few less steps you have to take in order to launch ECS. It's typically very fast to learn and very fast to launch and very easy to use. So in this case, what we're demonstrating is the ease of use of powering an entire ECS cluster using Graviton instances. And so the sample environment here is also in the form of a CDK deployment. So we have here the ECS Graviton Python file, which defines both an ECS cluster powered by Graviton instances, as well as a service to run on top of that ECS cluster. So it's going to utilize the same image that we built earlier in terms of the Node.js application that reports what processor architecture it's running on, but it's doing this on top of ECS instead of EKS, and this entire CDK deployment file is defining the end-to-end cluster that will spin up using the ECS optimized AMI for ECS, as well as the fact that it's using M6G 2 extra large instance type for the cluster. It also spins up an application load balancer to front the applications, very similar to the setup for EKS, and it sets up the rules, the listening ports, et cetera, that are needed to configure and deploy an application on top of ECS. So these are the steps that you would take. It's a very simple step. It's actually only one step to run, which is CDK deploy Graviton IDE ECS. It launches the entire stack end to end. Once that cluster is healthy and ready to go, we can query get the name of the load balancer and test our service as well. So let's go ahead and do that. Okay, so we've stashed the ELB name, and we can also run a very simple curl against it, just like we did with the EKS cluster. And in fact, here we go. We have 8 responses from our application load balancer, which is in front of our ARM64 containers running on the ECS cluster, and they're all reporting back that they are running on the ARM64 architecture. Let's just take a quick peek at the ECS cluster from the console. So we can see that we have our Graviton ID cluster here running in ECS. We have the one service, which includes one task, and we have one EC2 container instance powering our ECS cluster. Very simple to use, very intuitive, and we can see the instances themselves. We can see that this is a Graviton instance, in fact, powering this, and we can see the services and tasks that are running on that instance. Okay, let's take a look here. So we've successfully completed all steps of our workshop. Last thing I will call out is that you definitely want to make sure that you clean up your environment so that you don't pay for any applications or any pieces of AWS that are running in your account that you're not using, that you're not needing. They are the script here will clean everything up for you. You can simply just change into the scripts directory and execute cs_cleanup, and it will clean everything up for you. It's quite easy to use, and shut everything down and sort of go back and clean up everything that we've just built and created. I do want to thank you for your time. I hope that you had a good time walking through these steps. I highly encourage you as a next step to visit this workshop site if you haven't already. Again, graviton2-workshop.workshop.aws. Take a moment to go through this. Please head over to the AWS Getting Started for Graviton. Take a look there as well, and see how easy it is to use Graviton in your environment. So on behalf of Seth and myself, I want to say thank you for spending your time with us. I hope you enjoyed this, and have a wonderful rest of the day.